Hello, class. Welcome to this next lecture where we will be going through an introduction to scientific machine learning by looking at physics-informed neural networks. So physics-informed neural networks, as their name implies, is this first form of scientific machine learning where we're going to be incorporating physical equations such as, here we're going to be using Hooke's law to be able to help train a neural network in a way that's better than if we were to just use the data alone. So the reason is because in a lot of machine learning, right, the way that machine learning has really been built up is that it requires very big data. And in not every case do you actually have this data, right? So this data can be expensive. It could require the whole LHC in order to run and generate, or it could be something that is just simply unattainable, right? You might only have 5 data points. That might be as many galaxies as you can measure, so you're not going to get more. And in these kinds of cases, you can't rely on machine learning to be able to just simply solve the problem by having enough data, right? You don't have Google scale data, so what do? Well, the way that people traditionally solve these problems is they have used, scientific models and scientific simulation, right? Newton's laws and Einstein's laws of gravity, these things give you some very generalizable forms that can tell you what's going to happen at very large and very, very small time scales. You move to other types of physics, and these equations really tell you in a way that extrapolates fairly well how different systems will begin to behave, right? Like Newton's laws were written for a solar system, which ended up doing okay for a galaxy, right? It wasn't perfect, it wasn't exact, but these scientific laws, they tend to extrapolate fairly well because, there's a lot of philosophy around why, but a lot of people believe it's because of the parsimony of the laws, right? They use this idea of mechanisms, and they describe, this thing causes this thing causes this, and when we just know a few of the mechanisms involved, we can predict what will happen fairly well, right? So we usually call scientific modeling mechanistic modeling because it starts from mechanisms and uses these mechanisms to be able to predict how systems will evolve in a way where you can interpret all the terms. What we want to do now is we want to understand, how does machine learning play into this picture, right? What is machine learning in relation to mechanistic modeling? And how can we start to put mechanistic modeling together with the way that we are doing machine learning? So to start, let's start out by doing some machine learning. Let's learn what machine learning is all about. If you know this part, this might be a bit of a different introduction than you had to machine learning, because we're going to be laser focused on learning machine learning in a way that is appropriate for scientific machine learning. So what we start here with is we're going to have to add Flux. So I've already added Flux locally. The Flux is this machine learning package. So if I let me keep the same window here. If I look at, for example, flux ml.ai, then it takes you to this page where we can go. This describes the elegant machine learning stack, which we call flux.jl. And you can go, for example, to the documentation, which describes how the Flux machine learning library works. So for example, this is where you get all the information on loss functions. This is where you get information on nnlib, which has a bunch of these activation functions. This is where you'll learn all about how to do deep learning in Julia. What I'm going to do is I'm going to give a quick walkthrough into what deep learning really is by showcasing how this library is constructed, right? What are the basic parts of the library, and how are they actually put together? And if you understand how they're put together, then we can start to understand how to change this and how to become someone who's building something for scientific machine learning. So now let's look at training neural networks. Right, so training a neural network is really just the process of finding the weights that minimize a function. So let's say we want our neural network to be like the constant function 1, right? Because a neural network, remember, is a function, right? It takes in a value and it spits out some value. And so we can ask a question like, let's say, I want my neural network to act like the function that takes in any value and spits out 1. How do I find the weights that cause that to be true? This is the training process for this problem. So what I can do here is I can define a neural network, right? So this is a function that takes in 10 values and spits out 5. And then my loss function is take a bunch of, take 100 random inputs and see whether the value is close to 1. And what we want to do then is we want to minimize this loss, because when it's 0, that means that our neural network computationally acts like the function that takes in anything and spits out 1. So when we start, this loss is fairly high because the neural network with random initial conditions just doesn't have this behavior. And now what we can do is we can inspect Flux here. We could say, what is the training problem that I'm looking at? Well, the training problem is to take these numbers inside of these layers, right? So, if I look at the first layer, what is W matrix is, I want to choose all the values inside of here such that when I put in any value, it tends to spit out 1. And so what we can do is we can grab all of these parameters. This is what the params function in Flux does. It just grabs all of the parameters for one of these chain objects. And then we can call train. So what train will do is this here, I'm going to use the Adam method, which is kind of like stochastic gradient descent, which means it'll evaluate the loss function, and it'll evaluate the derivative and use that derivative to know in what direction it should be changing each of the parameters to decrease the loss. It will do that, and it'll change the parameters, and it'll check the loss again. It'll change the parameters, check the loss again. It'll keep repeating this process until the loss is hopefully very small. So let's see this in action. And not much to see, but then it just kind of trains. And then after it trains, we can check the loss function. Right, so note that the loss that we have here is stochastic because it is taking random vectors each of the times. Right, so every single run, it is taking 100 new random vectors. But still, if you're sampling the space in a way that, if you're sampling the whole space, then what you're really doing is you're causing the neural network to become the function, such that if you give it any value in 0, 1, then it will spit out 1, right? So it's really becoming the constant 1 function on this space. So we can see right here, this is our this is our progress meter, which is telling us how close we are to having this neural network trained. You probably don't need to do up to 10,000 iterations. This is kind of overkill. Let me actually explain. This little hack right here is that a lot of neural network libraries want you to give it a data set. Since the way that I'm defining the neural network is I want it to just be the function that outputs 1, there really isn't data that I'm working on, right? So I'm just saying repeat the empty data set, right? The empty tuple as data 10,000 times, and so this is just doing 10,000 steps. So here now I get a different loss function. We started with a loss function that was about 1,000, and now our loss function is on averaged all the way down to 1e minus 6. So this means that the neural network is a pretty good function approximator to being something that just outputs 1, right? Because if you put 100 values in there, each of these outputs are all pretty close to being 1. Let's actually kind of take a look at a few of them just to see. That's pretty close to 1. That's pretty close to 1, and if you keep on taking any values in that range, it tends to be like the function that spits out 1. So now let's ask a question, right? So why should we care about machine learning, and why are neural networks interesting? Well, what we did was we've just found the parameters that makes this function, right? This thing n of x be something that acts like the function f of x equals 1s of 5. How does that relate to machine learning, right? Because I did a few hacks in here, like I said, I put random data in there, right? So how does this actually relate to the real problem of machine learning? In any case that you have data, what you do is you assume that there's some underlying mathematical model, right? So if you have some data points x and y, what you're really doing is you're assuming that there is some relationship, right, from x goes to y. And if you're to know what that relationship is, right, then you can always predict y correctly, right? So if you had perfect knowledge and you knew this function f, that takes in x and spits out y, then you can always predict correctly. And the problem of machine learning is actually to find what that function is, right? It's a function finding problem. So why neural networks? Well, the reason why we use neural networks for machine learning is because of two properties, right? So the first one is known as the universal approximation theorem, which is, in simple language, that for any epsilon accuracy that we wish, if your neural network is large enough, so which means it has enough layers, these matrices, weight matrices are large enough, right? So either large in terms of the matrices or large in terms of the width, then it can approximate any nice function. So, any in some kind of, there are some caveats in there, but it can approximate any function within epsilon accuracy. So, if you take a space like 0 to 1, 0 to 1, this cube, you take any function defined on that. There is a big enough neural network such that if you choose the right values for all the weights, it will be within epsilon of that. If you want epsilon to be 1e minus 6, there is a neural network which is 6 digits accurate at every single point in that domain. So what this means is that we can reduce the problem of finding missing functions, right, the problem of machine learning, to a problem of finding the weights in a finite set of numbers, right? So this means that by using a neural network, we can transform this problem of finding a function, which is in some sense an infinite dimensional mathematical problem. We can make that be a finite dimensional optimization problem, which is find these numbers that define these values and weights such that it will be close enough to this function, right? And then when you find the neural network that has the same input-output behavior, you have something that is good at predicting. And that is machine learning, right? That's the way that you should understand machine learning mathematically. Now, why neural networks, right? Because there's a lot of other functions that do have this property of being able to be universal approximators. So for example, you probably learned in your analysis course that the polynomials, right, a0 plus a1x plus a2x, let me show the LaTeX here. You probably learned that this kind of function is a universal approximator, right? It's a universal approximator for any analytic function. And why is that the case? Well, because if you have an analytic function, this is the Taylor series, right? Similarly, you might have learned that a Fourier series can approximate any continuous function, right? So a Fourier series is you take the function and then you write out in terms of sines and cosines with a bunch of coefficients in front. So sine plus sine of 2x plus sine of 3x. If you put a bunch of coefficients in front of these guys, it can approximate any possible continuous function. And it even has a way to be able to handle discontinuities if you take enough terms, right? So these are ways to be able to do function approximation as well. So why isn't machine learning just using a Fourier series and just learning these coefficients a0, bk, ck, to be able to learn the input-output behavior for any possible function? Well, the reason is because when we define these universal approximators, when we do a lot of mathematics on them, a lot of these objects are one-dimensional. So how can you get to two-dimensional functions if you only know Fourier series? This process isn't actually too hard. You can just take a tensor product. You can actually show that this will give you a higher order universal approximator. So what does that look like? Well, it just means that you match, you take one approximator in x, you take one approximator in y, and then you take every combination of terms. So here we can take a polynomial, a second order polynomial in x, a second order polynomial in y, and then we have every combination of terms, and you can show that that is a universal approximator in 2 dimensions. But let's look at how many terms you start to get, right? So let's say you had n coefficients in each dimension. Well, if you have n coefficients in each dimension, then what happens is that you have to take every single combination of these input values, right? Because you can think about if you had x, y, z, then you need to have the x, y, z squared term, the x squared z, YZ term, right? You need to have every single combination. And if you remember anything about permutations and combinations, then you probably remember that these things grow factorially or exponentially, right? Because there's this relationship between exponentials and factorials through I'm forgetting the name of the approximation, but it's Stirling's approximation. So what this means is that if you have to take every single combination between all of these different values, then what you end up having is you have a process for creating higher dimensional functions, but this higher dimensional function approximator is something that grows in the number of coefficients that you need by the dimension to the dth power. So this is what we call cursive dimensionality, because it means that to go to higher dimensions, you get this exponential growth in the computational cost, in the memory cost, and everything that's involved in this function approximation. So the second property that makes neural networks applicable to machine learning is that they overcome this cursive dimensionality, right? So why is this needed? Well, I mean, if you have a Google-sized data set, then you have 5,000 inputs and you have 10,000 outputs. Well, you don't want something to the 10,000th power, right? Like something to the 10,000th power grows probably faster than what you'd expect. I couldn't even represent it here. Let me see if I use big here, that's how many coefficients you would need if you had 10 coefficients in each dimension. It's insanely large. It is unfathomably large. So you can't use an object that is growing with the dimensionality. But what you can do is you can use a neural network. And so there are some proofs in this area. This is one that I like to point to, which is quite explicit in showing that neural networks can overcome cursive dimensionality for any problem where Monte Carlo algorithms do. Though I will say that some of these proofs and even the theorem statements are not very accessible, but just there is a lot of work going on right now in the mathematics of data science, where this is one of the hot topics, where a hot topic is really just showing it in a lot of these cases that neural networks are an object that overcomes the cursive dimensionality. There isn't like a proof in the general sense of this, but people have shown in a lot of different cases that neural networks overcome cursive dimensionality, which means that what they're basically proving is that the number of the computational cost, or the number of coefficients that's needed for a dth dimensional function, grows as a polynomial in D instead of exponentially. What that means is that this is something that is strictly a slower growth than exponential. And so there is a amount of dimension, right? There is a dimension size D such that using a neural network will become more efficient. Usually what I kind of see is there's some reasons from multidimensional integration cases where we can kind of see like 8 or 10 dimensions is kind of where the cutoff really kind of is, where, if you're at that size, neural networks or these universal approximators in these other forms are much more efficient than just doing tensor products between all the dimensions. So this means that, if you have a one-dimensional object, use a Fourier series. If you have a two-dimensional object, maybe Fourier series works out, when you do a tensor product. 3 dimensions, 4 dimensions, it starts to be, neural networks start looking good. Sometimes they're doing better, sometimes they're not. It can be very problem dependent. By the time you get to about 10-dimensional objects, it becomes very clear that neural networks start to perform better. So there are a few other properties that we can consider as well. So for example, the assumptions in a neural network can be encoded in its architecture, right? They have a lot of flexibility in that sense. So if you make the last layer that comes out be something that squares the output, then since you're taking the square, the output has to be positive. And so this is a nice way to make it so that way you have a universal approximator for positive functions. And so, no matter what weights you choose, you get a positive function. And so it's a good way to learn a positive function. If you want your function to be smooth and have all your derivatives defined, you can choose tanh activation functions, or you can choose anything that is a smooth activation function. Right? If you want your output to be between 0 and 1, you can choose a sigmoid in the last one. Right? So there's a lot of different activation functions you can choose to really kind of change a few of these properties in your neural network and kind of refine it towards your problem. Another very nice property that they have is that it's more of a, what properties do the classical basis functions not generally have? And it's that if you tensor two different objects, if you tensor something in the x direction, the y direction, then you have perfect, perfect good properties. You have, exponential convergence with Fourier series in the x dimension. And you have exponential convergence if something only has y values. But if something does not hit the way that you did the combinations between x and y appropriately, then you can have very poor convergence. And there's this very wonderful talk by Nick Trefethen, which goes into this property and how it's actually one of the defining issues in multidimensional integration or cubature methods. So for example, if you have sine of x, sine of 2x, sine of 3x, and you have sine of y, sine of 2y, sine of 3y, going down these two dimensions, then you have all multiplied combinations of them. It turns out that something like sine of xy, right? You have sine of x times sine of y, which is different than sine of xy, and representing the function sine of xy can be very difficult in this basis. This is basically due to kind of missing the symmetry, where the axes of your basis are much better represented in the way that you've chosen to do your representation, and so there are some functions which are harder to be able to get in a classical basis representation. It turns out the neural networks, right, because they're not really aligned to a basis, right? The first thing that you actually do with the input is you're multiplying by a matrix, which is essentially a rotation. Right, so you're rotating it onto kind of whichever basis you want. You do nonlinearity, which is kind of warped space, and you rotate it again, you nonlinearity, and you keep on rotating. So whatever basis the data actually really does lie on, it kind of matches it. And so it doesn't have this property that it does some areas better than others, unless you choose activation functions to enforce that. One of these other properties that makes neural networks nice is that they're very easy to compute with, right? There's good software for them, right? PyTorch, TensorFlow, Flux, all these things already exist. And they're GPU accelerated, right? Because everything uses matrix multiplies. We'll go into the speed of matrix multiplication as one of the topics that we look deeply into for parallelization. Basically know that matrix multiplication is probably the most studied problem for something to optimize. And so if what you're building your object on, your computational object, is just matrix multiplication, then you're looking at probably the most optimized part of parallel computing that's ever been done. And neural networks essentially just are matrix multiplication repeated many times, right? So it basically is just kind of playing into this is what we know how to compute well. Well, we define a universal approximator which uses the thing that we know how to compute well. And lastly, another property that not as many people know about is that there's a lot of papers around which kind of show that local minima are the global minima of a neural network, which means that if you do local optimization, you will tend to get optima that are very close to the global optima. And if you have an infinite-sized neural network, that local optima is actually equivalent to a global optimum, which means that if you do local methods like gradient descent, you can abuse this property, and whatever weights you get to is good enough. And not only is it good enough, it's probably just as good as if you're to do a much more expensive procedure. So you can use your really easy computations of matrix multiplies on GPUs, and then you mix this with a really cheap local optimizer. And for some reason on neural networks, this gives you an algorithm that is not only good for computation, good for parallelism, but also is quite robust because of this last property. And so this is kind of why neural networks are used, right? So high dimensions, also very good for computation. There are other networks that you can, or there are other types of universal approximators that you can choose, and a lot of scientific machine learning is coming up with these other approximators. So what this is really doing is, so machine learning is then all about learning missing functions. And what we want to do for scientific machine learning is we want to bring the structures of science in as some of this extra information for how we're doing this training process. And so scientific machine learning is neural networks and machine learning mixed with scientific computing, right? So scientific computing is this discipline that is focused on scientific simulation. It's not to be confused with computing just generally done in science. This is actually a very technical term. Let me just kind of showcase here. Scientific computing is this very technical term for a very computational science, scientific computing, which covers the scientific simulation algorithms that are traditionally done, which is like using Taylor series, automatic differentiation, finite element methods, integration, Runge-Kutta methods for ordinary differential equations. You'll see that the term differential equations shows up in pretty much all of these, right? Time stepping for dynamical systems and differential equations. The differential equations kind of show up everywhere here, because they're kind of the basis for a lot of scientific simulations. So one thing that we should probably ask very early in this course then is, why do differential equations come up so often? Is this something that we should expect, or is this something that might go away, right? The answer is actually, that's kind of a deep question, like why does science always end up with differential equations? But it has a very simple answer. And that's really that, when you do a scientific experiment, you take a system, right? And then you do a small nudge to it. You always are doing a change, and then you measure how much of a change you did, right? So you take a system and you say, this is in non-dimensional terms, this is force 1. And now when I put more force onto it, what happens? Well, it moves. When I put even more force onto it, what happens? It moves some more. And so what you're really doing is you're taking your system, and then you're seeing, if I'm to change the input, how much of an output change do I get? And so the equations that you get, the scientific laws that you get, everything that comes out of this differential equation, or that comes out of these scientific studies, these measurements, are relations between changes in the input to changes in the output, and the type of mathematical equation you have when you know about how the changes in inputs are related to the change in outputs is a differential equation. Right, so you see them everywhere in scientific laws for a reason, right? It's because the way that we do science and the way that we generate measurements and outputs is a process that is essentially geared towards giving us differential equations. So what we want to kind of do then is we want to, we understand that a lot of these physical differential equations, is there a way to be able to put a physical differential equation into the way that we're doing machine learning such that we can do machine learning with less data, right? This is then the goal of scientific machine learning. And to figure out how to do that, we will first just have to figure out, how can we solve an ordinary differential equation with a neural network? Like, what does that mean, and how can we do this process?